now that we're in Algebra 2, we're going to go and we're going to look at trig in ways that you have not before in geometry class. So in order to do that, we're going to have to refresh our memory about special triangles. There's two special triangles that we tend to study. One of them that's pretty straightforward is the 45-90 triangle. And it's called such because it has two 45-degree angles in it. Now, both special triangles that we're going to look at are right triangles, so they both have a 90-degree angle. So the other two have to add up to 90 as well. Now, there's some interesting things that come from this idea that the two angles are 45. For one, we know for a fact that this is an isosceles triangle, and so since those two angles are the same, these two sides must also be the same length. So that's useful. The other thing that we know is that if well, we could figure out the length of this side and how it's related to these two guys by using Pythagorean theorem. For now, let's just call the hypotenuse the hypotenuse. And if we want to figure out what this is in relation to these two x's, we'll use the Pythagorean theorem. And you'll recall it looks a little something like this. C squared equals a squared plus b squared. Good old Pythagoras. Thank you, buddy. About 2,000 years ago. That's some old stuff. Anyways, so in our case, we have the hypotenuse, and it's squared. And that is equal to, in our case, x squared plus x squared. Hey, that we might be able to use some skills that we've had from the past to simplify this a little bit. For instance, we know that if we add x squared plus x squared, that's 2x squared. Hey, some of this basic math might come in handy. The other thing is that if we well, we'll just go ahead and write hypotenuse squared for now. The other thing is, though, is we can get rid of that hypotenuse squared by taking the square root of both sides. And so when we do, we end up with just the hypotenuse. And if we want to know what the hypotenuse is, it's square root of 2x squared. Now, something else that hopefully we recall from our study of radicals is that we can go ahead and break this apart. There's an x squared here inside of a square root. We can go ahead and take that outside. So that's x times square root of 2. So if we want to know the relationship between the hypotenuse and the sides, well, it's this. It's x times square root of 2. Whatever the length of the side is, we just multiply that by square root of 2, and we get the length of the hypotenuse. That's pretty darn cool. Now, what that means is, quick practical application here, is if we have a triangle, and we happen to know that one of the sides, and we know it's 45, 45, 90, we'll assume that it's 45 here, and we know one side length is 5, guess what? That means that we can assume that the hypotenuse is going to be 5 square root of 2. That's pretty darn cool. The other neat way we can use this is that if we have a right triangle, and again, we know that it's 45, 45, 90. If we happen to know that the hypotenuse is 7 in length, then we can figure out what either of the sides is by this relationship as well. In other words, if this guy is equal to x times root 2, then this side over here must be equal to 7 divided by root 2. Interesting. Now, only one last little fancy thing that I'd like to remind you folks of is, and let's go ahead and put some dividing lines in here so we can separate this out. We had some really good stuff earlier where we were deriving the hypotenuse using Pythagorean theorem, but these triangles are kind of separate examples all on their own. Remember 7 divided by root 2? We'd still like to know that there's another version of that. We can rationalize the denominator by multiplying the top and the bottom by root 2. And if we do that, we end up getting 7 root 2 over 2. So I just wanted to remind you that may come into play as we work on trigonometry using special triangles. So this is everything I wanted to say for now about the 45-45-90 triangle, but I'd also like to discuss the 30-60-90. So in a 30-60-90 triangle, there's some stuff that we're going to have to remember, and I'm going to try to present this in a way that will help you to remember this later. Instead of just pure memorization, we're going to try to remember a few things and put them together so they all fit. In a 30-60-90 triangle, it turns out that the 30-degree angle is very small, and so the side that is opposite or across from the 30-degree is the shortest side in the 30-60-90 triangle. And the side that is across from the 60 is a little bit tricky to remember, but the hypotenuse itself is so long that it's double the length of the shortest side. So I'm going to go ahead and just say the hypotenuse is 2x. So what we'd like to figure out is this missing side over here. And we'll go ahead. Remember Pythagorean Theorem, we say that c squared equals a squared plus b squared. So if we can at least remember that the shortest side is like 1 and the longest side is twice that, that'd be a great starting point. And then we could always figure out this side if we had to. So let's go ahead and try it. So we know that our hypotenuse squared would be something like 2x in parentheses squared. And then we've got this side we know is x squared. And then we've got something else that is also going to be squared. I don't know what to call it for right now. It's a missing side. If you don't mind, maybe I'll just call it m for now. So we'll just say this guy's m. So we'll say m squared. And then what we'd like to do is solve for m. So it'll be m squared equals x squared minus parentheses 2x squared. Don't forget that since that's all in parentheses, we got to square the 2 and the x, properties of exponents. So this will be m squared equals x squared minus 4x squared. And oh, thank you. Somebody just called in to let me know that there's a problem with this video. I made a little mistake. Sorry about that. Let's fix this up. What it really should be is m squared is equal to 4x squared minus, I mixed it up. If I want to get this x squared on the other side, it'll be 2x squared minus x squared. So 4x squared minus x squared. Thank you for that call in. Appreciate that shout out. Anyways, so now let's go ahead and get the square root of both sides so we get m all by itself. And when we do, we get this. We get m, and it is equal to 4x squared minus x squared is just 3x squared, and we just get the square root. Now again, that x squared can come out of the square root, and so what that gets us is x times square root of 3. So for those of you who have seen this before and you kind of knew that there was going to be a square root of 3 coming up, now you know where that came from. We get, if we call the shortest side x and the longest side 2 times x, then this other side, the side that's across from the 60-degree angle, is going to be x times square root of 3. Now again, we can use that information to solve practical problems. So what kind of practical problems might you ask? Well, if we happen to know that we have a 60-degree angle in a right triangle, and we happen to know that the distance on the ground from here to here is 5, and we wanted to figure out what is the height of this building, and we're over here and we're looking up at a 60-degree angle and we see the top of the building, we can very quickly get the idea that that this building, the height, is going to be equal to, actually let me get rid of the x because I don't want to confuse it with this, but it'll be just this guy times square root of 3. So the height here will just be 5 square root of 3. That's pretty awesome. If you just know you're looking up at a 60-degree angle and you know this distance that you are from the building, the building must be a height of 5 times square root of 3. Let's call it meters, just to make it fun. And then another thing that's kind of interesting is what if we had something like this? Let's see if I can, let's make this. Oh, one thing that I really want to strongly encourage you folks is that when you're drawing your 30, 60, 90 triangle, try to make it real obvious that the smaller angle is the 30. When you draw it, kind of try to draw it to scale, and that the larger angle is 60. So you can see in this one, it's a very narrow angle where I have the 30, and it's a wider angle where I have the 60. If you do that, you'll have a better sense of what's going on. So let's say we have a situation like this, and we happen to know this length over here. So for some reason, we know that we're looking up at a 30-degree angle, and we want to try to measure how tall this tree is before we chop it down. What we might do is we would say, what if we were, I don't know, 20 meters away, and we wanted to figure out what the height is over here? What we would do is we would say, well, this would be equal to x times square root of 3, and this is normally x over here. So what we do is we say, well, our height must be equal to, let's see, we'll solve this equation here. X root 3 equals 20 is the same as x equals 20 divided by root 3. So yay, so we just figured out that our height must be equal to 20 divided by root 3. Yay. Okay, we can do that. Now again, just like I showed you before, we might want to rationalize that denominator. So if we have 20 divided by root 3, we can multiply by root 3 over root 3, and that gets us 20 root 3 over 3. So don't be surprised if you are asked to recognize the value of a sine or a cosine either in this form, 20 over root 3, or this form with the denominator rationalized. Okay, that's it. That's all I had for you for 45, 45, 90, and 30, 60, 90 triangles. Next thing is we're going to use the knowledge of these guys in order to figure out sines and cosines, exact values of sines and cosines.